Welcome to Science and Engineering World, where we use the principles of mathematics and science to think engineering, act engineering, and practice engineering. In this presentation, we want to use a practical scenario to demonstrate some effects of fluid pressure. My name is Olutola Fakehinde. Surfaces are horizontal, vertical, inclined, and even curved. And fluid always has significant effects when it is in contact with any of the surfaces. We want to examine fluid pressure force on vertical and horizontal surfaces in this presentation. In a serious accident like this, can the driver in this car escape on his own effort? Let's examine this. The scenario here is that a car with a mass of 2,200 kg runs off the road in an accident and lands at the bottom of a lake 6 meters deep. The dimensions of driver's door are 1.2 meter long and 1.1 meter wide. Some 4 pertinent questions come to mind. Welcome to part 3 of a practical scenario of the effect of water on surfaces. Before we move on, kindly subscribe to this channel if you have not done so, and press the notification button which is on the bottom right corner of your screen for notices as we post videos on this channel. If you are subscribed, thank you. So we'd like to encourage you to please continue to share these videos and other videos on this channel so that we can spread to the other part of the world. And I really appreciate you for doing this. Thank you. Now to part 3. We have done part 1 and part 2 for this scenario. And in part 1, we were able to establish some principles and assumptions that helped us in solving some of the problems in these scenarios. So I'm going to put the links to part 1 and part 2 at the top here and at the bottom in the comment section. However, because of the fact that these principles and assumptions established in part 1, we cannot go back to them now, but we need to be able to follow us. So try and look at those part 1 and part 2 before coming to part 3. We'll do a quick recap of part 1 and part 2. Here we saw the car at the bottom of the lake, and then we were able to calculate the forces or establish some forces acting on the door. And we saw that the water was exerting a pressure force of 77 kilonewton of the door. And then the driver was trying to escape in the car with a 1 kilonewton. Here we were able to conclude that there is no way the driver can escape on his own with this effort of ease of 1 kilonewton against 77 kilonewton. And then we went further to see if he could escape if the top of the door is at the level of the water. Here we also established that the water was exerting a force of 8 kilonewton on the door from outside, and the driver was exerting his 1 kilonewton in the inside. Again, we found out that it's not possible for the driver to escape here with his own effort of just 1 kilonewton. So the question now is, at what point could he possibly escape? We saw he couldn't escape where the car was at the bottom. He couldn't escape when the door was at the level of the water. So in that case, it means for the driver to be able to escape at all, he could have done so before the car is completely immersed in water. So the question now, which is question 3, is that if he couldn't escape at the bottom and he couldn't escape when the door was at the same level of the water, at what point could he possibly escape with his own effort? Let's examine this. The first thing we want to establish here is that for the driver to be able to escape from the car, then the force of the water on the door must be less than the force of the driver. This is to say that the force exerted by water, Ft water, must be less or equal to force exerted by the driver. From the previous video that I put the link at the top, we have seen that the force exerted by water is given as gamma H bar A, and the driver's effort is given as 1 kilonewton, which is 1000 Newton. What is A? What is H bar? In the previous video, we have seen that the area we are looking at is a wetted area of the door. That is the area that the water is in contact with on the door. So this will be our area A. We have seen here that the width of the door will still remain the same, which is 1.1 meters. That's the width of the door. But the height will now depend on how far the water is on the door. That is, H will now be from here to there. So this will be our H now. So we need to find the H at this point. So area is giving us 1.1 times H. That's the area. Again, we know that H bar from the previous video, that H bar is the center of the area, the center of the height touched by the water. So which means H bar will be equal to half of H. We also know that gamma, which is the specific weight of the water, is given as 10,006.2 Newton per meter cube. With all this established, we can now put them inside this expression, And then we now have FT water will be 10,000 and 6.2 times H bar we have seen is 0.5 or 1 over 2 H, and the area is 1.1 H, and all of this will be less or equal to the effort of the driver. Putting the data in the left hand side into the calculator, we found out that we have 5,503.41 H squared to be less or equal to 1,000. Dividing the left hand side by 5,503.41 H squared divided by 5,503.41, we see that this is equal to 1,000 also divided by 5,503.41. So H squared equals to 0.1817. Again, we need to find the square root of H squared to be able to find H, and we must do the same on the right hand side. So we say square root of H squared will be equal to, we are going to have two roots here, so we can have plus or minus 0.1817. H is equal to 0.4263 meters. Now we see that we have plus or minus because we should have two roots here. Because we are talking of height, the negative will not be useful for us in this calculation. So the height of the water on the door should be about 0.4263 for the driver to be able to escape at all. Now, let us establish the force that is being exerted by the water with this height here. All we need to do is just plug in this value H that we have into the expression we have above. That is, plug it into that because that's the effort of the water. Verifying the force of the water on the door at this point, we now have FT water will be equal to gamma A H bar. H bar is half of H, which is equal to half times 0.4263. So H is 0.4263 0.21315 meters. That's H. What about A? That's the area. A will give us 1.1 times H, which is 1.1 times 0.4263, and A now gives us 0.4646893 meter squared. So that is A. So now FT water will now be equal to gamma we know as 10,000 and 6.2 times area 0.46893 times H bar 0.21315. This gives us 1000.144, and the unit is Newton, like we have seen before. So we can say approximately that the force of the water on the door is equal to 1 kilonewton, and this corresponds to the force of the driver, and so this is equal to the force FT driver. So like we have said earlier, the force of the water must be less or equal to the effort of the driver for the driver to be able to escape. Let us find the center of pressure at this point as well, because it's also an important point that we need to know. Calculating the center of pressure, we have HCP, that's the center of pressure, equals to H bar plus IG over AH bar. So we need to find IG. And what is IG? Which is the second moment of area of the weighted area of the door, which is this area now. That's area. And we have our base here to be fixed, which is 1.1, and then the height, which we have seen as 0.4263. For IG, because it's a rectangle, this will give us the base times the height cubed over 12, and that gives us 1.1 times 0.4263 cubed over 12, and we have IG equals to 0.0071 meter 4. H bar we say is equal to 0.21315 meters, and area we calculated it to be 0.46893 meter square. All right. So we now have the center of pressure HCP to be equal to 0.21315 plus IG 0.0071 divided by area is 0.46893 times H bar, again 0.21315. This gives us 0.21315 plus 0.071. Therefore, HCP equals 0.2842 meters. The center of pressure we just calculated is not this one here, where the effort of the water is applied. We have also seen in the previous video that HCP is equal to 2/3 of H. So let's see how far it agrees with the result we got above. So we now say this is equal to 2/3 times H is 0.4263, and putting all that into the calculator, we also obtain the same value, 0.2842. So we have the same center of pressure. From the value we obtained above, that FT water is approximately equal to 1 kilonewton, and this is equal to the force of the driver, FT driver. We also obtained that the center of pressure, HCP, is 2/3 of H, which is equal to 0.2842 meters, which is below the center of gravity, H bar, as expected. So we can now say it is most likely the driver is able to escape here when the water level H is 0.4263 meters from the bottom of the door up. In order to conclude on this question 3, it will be good to have the percentage of the wetted area to that of the door. So we can now see the door, the car door on the left, and the wetted area, which is also part of the door now. The door area AD is equal to 1.1 times 1.2, which is 1.32 meters square. The wetted area A water is 1.1 times 0.4263, and this gives us 0.46893 meters square. We can now compare the two by looking at the percentage of the wetted area to that of the door. So percentage of the wetted area to that of the door will give us a percentage of wetted area to door will give us the area of the wetted surface 0.46893 divided by the door area 1.32, and this gives us 0.355. So the percentage will now give us times 100 and that will be 35.5%. So this tells us that if the wetted area is more than 35.5% of the door, then the driver will need external assistance to be able to come out of the car. So we now go to the last question, which is question 4. The last task in this practical scenario is question 4, which says, what is the maximum energy required to recover the car from the bottom of the lake? We shall take an assumption here, and that assumption is that the car can be assumed to be a rectangular flat plate at the bottom of the lake with the dimensions as on the schematic diagram. There are two forces to be considered on the car. The first one is the weight of water that is sitting on the car, which is the force due to the water on the car. And the second one is the weight of the car itself, due to the mass, so force due to the mass of the car. Both of them are acting vertically downward. So let's consider the first force, which is the force of the water on the car. The total force of water on the car is given by the formula we've been using before, which is Ft, that's total force of water, which is equal to gamma A H bar. Gamma we know is a specific weight of the water on the car. That's gamma, which is given as 10,000. We have been using this before, and 6.2 Newton per meter cube. Area is the area of the plate. Now we assume the car is a flat plate, and it is given as 4.5 times 1.85. And this gives us 8.325 meter square. Since we've taken assumption that the car is a flat plate lying at the bottom of the lake, so it is taken as a surface that is horizontal to the action of the water on it. We now say that H bar equals to the depth of the water from the free surface to the lake, to the bottom of the lake. That's 6 meters. So now Ft water will be equal to 10,000 and 6.2 times area 8.325 times 6, which is H bar, and this gives us Ft water on the car will be equal to 499,809.69, and this is in Newton. So this is the force of water acting on the car at the bottom of the lake, and it is acting downward. So let's call this force 1. The second force is the force due to the weight of the car. It is a gravitational force, so we call it Fg, which is given as mass times acceleration due to gravity. So the mass is given as 2,200 kilogram, and the acceleration due to gravity is always taken as 9.81 meter per second. So this Fg will give us 2,200 as the mass times acceleration due to gravity, 9.81. So Fg is now equal to, putting all of that into calculator, we have 21,582 Newton. You can call it force 2. The total force on the car will be sum of F1 plus F2 that is total force equals to 499,809.69 plus 21,582 00. So adding this up will give us the total. So we now have 69,193,1 2 and 5. So this will be the total force acting on the car, which is also the weight of the car and the force due to the water in Newton, and this is acting downward. So to find the energy required to bring the car up, we know that energy is work done. Energy is work done and work done is force times distance. In this scenario, we need the equivalent of the Ft above to be able to bring the car up. So the force is Ft and the distance is the depth of the lake. So the distance will be h bar. So we now have here 521,391.69 times 6, which is the meter, Putting this in the calculator, we have 3,128,350.14, and that gives us a unit of Newton meter, which is the same as joules or joules. Writing this in engineering notation, now I have 3.128 times 10 to the power 6 joules. So the energy required to bring the car up is energy can be approximately 3 megajoules. This is the least amount of energy required to bring the car up from the bottom of the lake. Okay, we have seen theoretically that the driver can still escape with just small part of the door in the water, like about 30% in the water. A big question is still there, which is, can he escape? Let us discuss this in the comment section below, because there are so many factors we still need to put together to come to that conclusion if he can escape or not. Meanwhile, we want to appeal to drivers to please be careful on the road. It's going to be a very big disaster to find oneself at the bottom of the lake or any water for that matter. So let's be careful. Well, if you enjoyed what we have done so far and you find this video very useful, please do 4 things for me as usual. Number 1, like the video with a thumb up. Number 2, share to others to enjoy the same benefit we are enjoying. And number 3, comment. We want to have your feedback. We want to discuss, like we have said, whether this driver can still escape. There are so many factors for consideration. And then number 4 is that please subscribe to this channel. Your subscription will take us far, and if you have not subscribed, there is a small button here below on your screen. Please press that button now so that you will be able to encourage us to do more video. And like I always say, think, act, and practice engineering. And then until we meet again for another topic, keep studying.